everybody. Good afternoon. Bear with me, this is the first time I've done an actual physical talk in about 2.5 years, so this is a bit weird for me. My name's Lee Coleman. I am a software engineer and developer advocate for IBM, and today I'm going to talk about some of the different things we can do as software engineers to get the most out of our applications. Right, so what we're going to be looking at, we're going to look at why the JVM is important. Being Java developers, we generally all use a JVM. How the cloud has changed the characteristics of the JVM over the last few years. I'll give you a little bit of an overview of some of the most popular JVMs like Hotspot, OpenJ9, and Cryo. I'm going to talk about picking the right runtime because it doesn't matter what you do to your JVM or what JVM you pick. If you're using an inefficient runtime, then you're not going to get the benefits of it. Then I'm going to talk about some of the tweaks we can do as software developers. Talk a little bit about what class cache sharing is, and I'll give you hopefully a little demo of that. I'll talk a bit about what idle tuning is and what the JIT server does. And it's not just OpenJ9, other JVMs also have the JIT server technology. And then if you were here for the previous talk, they talked a little bit about Cryo and things like that. I'm going to talk a little bit about that as well at the end and things like that. Right, so let's get going. Why is the JVM important? Well, as Java developers, our code generally wouldn't run without the JVM. So a bit of an overview of what a JVM is. It's a virtual machine. It's responsible for taking your application bytecode and converting it into machine language. The great thing about the JVM is essentially it can kind of run anywhere, hence the phrase that we use with Java, write once, run anywhere. So why do people use JVMs? I mean, they've been around for quite a while now, 20 plus years. The great thing is they're cross-platform, like I mentioned. They have a large library ecosystem. They have great garbage collection, which you can tune as well. They have some amazing monitoring tools if you really want to see what's going on inside. And they're proven and robust. Enterprises have used JVMs and Java for a very long time, so we know it works and we know it works well. So the architecture of a JVM, you kind of have 3 levels. You have your class loader subsystem, you have your kind of runtime data area, and then at the bottom you have your kind of execution area. So the class loader subsystem is responsible for loading, linking, and initialization. The loading part essentially loads classes using 3 different class loaders: Bootstrap, Extension, and the application class loader. Linking basically verifies the generated bytecode, prepares all the static variables, and assigns values and resolves any symbolic memory references. And then the initialization part essentially assigns static variables with their original values and executes the static block. So if we go down a level to the runtime data area, this is responsible for different things. So the method area stores metadata, the constant runtime pool, and the code for your methods. The heap part is a common memory shared between multiple threads, and it stores objects, instant variables, and arrays. Then we go to the JVM language stack, which is created when a thread is created, and that stores local variables. Then you go down to the PC registers, and that's every thread has its own register, essentially, and this stores the address of the Java virtual machine instructions, which is currently being executed. Then, lastly, we have the native method stack, and this holds native method information. So for every thread that's created, a new native method stack is created. Then if we go down to the last level, this is the part that's kind of responsible for executing our code. So it reads the bytecode code and executes it using the interpreter and the JIT compiler. So the interpreter interprets the bytecode faster, but executes it a bit slowly. The disadvantage of the interpreter is that when one method is called multiple times, every time a new interpretation is required, whereas the JIT compiler neutralizes the disadvantages of this. The execution engine will be using the help of the interpreter in converting bytecode, but when it finds repeated code, it uses the JIT compiler, which compiles the entire bytecode and changes it to native code. And native code runs a lot faster. So you have your native method interface, the JNI. This interacts with your native method libraries. And then you basically just have your native method libraries. So that's a bit of a little overview of the JVM without going into too much detail. Now let's look a bit about how the cloud and the JVM has changed over the years. So a lot of people don't think about this. You all get preached about, saving money, saving resources, but what does that actually correspond to? Well, if we're saving money on the cloud, we're also saving energy. And as engineers, it's kind of our responsibility to do something about this. We're responsible. I mean, I don't know if you've seen a data center, but they consume humongous amounts of power. Now, once a company's set up a data center and it's all ready in there, the main cost afterwards is electricity usage. So as engineers, if we can save, make our applications a bit more performant, a bit more robust, we can save a bit of energy as well. So what does the cloud kind of offer us? So if you consider this graph, this is kind of like, imagine you've got your own data center in your building. The problem is with that, you have to have the hardware resources to manage peak load. So when it's a public holiday or something like that, and everyone's, say, using your shop, you have to have that hardware there. But most of the time, it's not being used. So it's a pretty waste of resources that you can't share. Now, if we move to the cloud, and imagine we're still using monoliths here, if we move to the cloud, now we can free up some of those resources. So hopefully save us a little bit of money because we don't have to buy all this stupidly expensive hardware and have it there all the time. But we can also free up resources for other people in the world to use. And that's basically how cloud providers do it. Amazon started this years ago where they had free resources in their data centers. So why not start, selling these to people? And that's kind of really where the cloud started to become a thing. Now, if we move down to like microservice architecture, we have a lot more granular control over our applications. Again, as you can see, we're freeing up more resources for people, hopefully freeing up a little bit more energy, doing our part to save the planet. And also, because we've got granular control, we can basically, scale up and down very quickly to basically save resources as quick as possible. The time it takes an application to start up is complete wasted time. So we want stuff to start up quickly and shut down quickly to save our organization money, save ourselves money, and also save some energy. So Kubernetes is great, and microservices are great, but we have a big overhead here. We have a JVM in every container, whereas, say 10 years ago, 15 years ago, we would have loads of runtimes, or one runtime running on a JVM with loads of applications, whereas now we are putting a JVM in every container. That is a massive overhead. So what does that mean? That means people that create JVMs have had to change the characteristics of a JVM. So basically the problem is here is you change one of these characteristics and it can have detrimental effects on other characteristics. And I think in the cloud, the main things we're looking for is stuff like startup time, footprint, ramp-up time, response time, and CPU usage. But again, changing one of these characteristics has effects on the other characteristics. So getting this balance right can be difficult. So hands up here. Who had this phone? Who remembers this phone? Anyone in here? Awesome, yeah, amazing phone. I think, yeah, used to play Snake on it all the time. This was my first mobile, so I'm not quite young enough. I'm not young enough to not have seen this phone. I did have this phone. But this had Java Me inside. And the characteristics of this kind of Java was small footprint, fast startup time, and quick and immediate ramp up. Because at the end of the day, if I'm, say I load up Snake and basically it takes a minute before my game is fully loaded and my Snake's not drilling around the screen. Imagine playing Call of Duty or something like that, and for the first 5 minutes of your game, you have really bad latency because stuff's starting up. That's just not acceptable in today's world. The difference here is back then, we were really constrained by the hardware that was available, whereas now we're more constrained. We have the hardware. The cloud has all the hardware we need, but we're basically trying to save money. So if we compare this to kind of a JVM in the cloud, as you can see, the very similar characteristics: small footprint, fast startup, quick and immediate ramp up. And like I mentioned, the time it takes your application to start up is really wasted time completely. If your application takes 5 seconds or 10 seconds or a minute to start up, that's completely wasted resources. Nobody can use your application until it's fully booted up. So this is something you really need to consider when you're thinking about a cloud native approach. So why should developers care about optimizing our applications? It doesn't save that much money. I mean, it's our organizations that are paying for it. It's not coming out of our pocket, so why should we care? Well, let's put a few things into perspective. There's over 500, so over 500,000 data centers in the world. This includes smaller ones in your organization and bigger ones. The area of land they consume is equivalent to 6,000 football pitches. And I'm in America, so I'm going to say soccer pitches, just so you know which type of football I'm talking about. And this data was taken in 2019, so it's probably a lot more now. But in 2019, the UK's energy consumption, I'm talking England, I'm talking Scotland, I'm talking Wales, and I'm talking Northern Ireland, times that by 1.5, and that is the energy data centers are consuming. We don't see this. This is all happening in warehouses. We don't see it anywhere. But that is what we are sucking out of the planet in terms of energy with these data centers. And we may be a bit more aware, being software engineers, but the normal consumer of our goods, the person using, say, Facebook or Twitter and all these services, they have no idea what's going on in the back end. They have no idea that these humongous data centers are consuming all this energy and essentially running their applications. Now, luckily, the hardware engineers are doing their part, and thank God they are. So they have made massive, massive improvements over the years. So as you can see, they've managed to flatten that curve. But if we carried on using the same hardware and using the same efficiency of the hardware that we had in 2010, as you can see, the energy consumption of these data centers would have gone through the roof. Now, the hardware engineers have done their part. It's now time for us as software engineers to try and do our part a little bit. So hopefully that kind of cemented a little bit of why it's important for us, because again, we are engineers. We are the ones that hopefully are going to save the world. But there are lots of different JVMs available. So it's all well and good saying this, but if you pick the wrong stack to use for what you're trying to use it for, then it's going to be inefficient. So there are JVMs for absolutely everything, IoT, all kinds of different things. I love things like the Wonka JVM. I think that's an awesome name for a JVM, and Squawk VM and things like that. But yeah, there's loads of different JVMs. One of interest is the Maxime JVM. This was created by Manchester University in partnership with Oracle. And this is basically what GraalVM has come from. So I don't know if any of you use Graal, but that is pretty much what the GraalVM is based on. Now, when they built that, the cloud wasn't really a thing, and what it was providing wasn't really needed at the time. But now we're in kind of this new world of cloud native technologies where we want our stuff to boot up quickly. The kind of what GraalVM stands for is a lot more important these days. So these are some of the most popular JVMs. I presume some of you have used some of these. Oracle, you've got the one from Amazon. There's also one from Microsoft these days. I think they're based on the OpenJDK JVM. Azure's got its own one as well, Graal, and of course there's Clip's OpenJ9, which is now, I think, called Cemaru Runtimes. So I'm going to give you a bit of an overview of these three JVMs and the benefits of them. Well, Hotspot's been around for a while, as we all know. Its original release was in 1999. It was created by Sun Microsystems. And in 2006, this was open source. And this was an amazing thing because it meant that organizations and other people around the world could take this JVM, take this technology, and put their own stamp on it, configure it, and make it work in the way that is required for them. Hotspot continuously, essentially, analyzes your program's performance for hotspots, hence the name, which are executed often or repeatedly. And these are targeted for optimization. So this is really where the hotspot name came from, and this is why it became a very good and used JVM. OpenJ9 was open sourced by IBM, I think, about 4 or 5 years ago now. It was one of the biggest open source contributions in history from IBM. Millions of lines of code this was. And this has been used by enterprises around the world. Now, IBM has had to go in and change a lot of things here because of this new kind of cloud-native world, which means they've had to change the characteristics of it, but for the better. So as you can see, Hotspot's kind of startup time, which I mentioned is very important, is half of what Hotspot is. OpenJ9 is half of what Hotspot is, sorry. 50% smaller footprint on startup. Like I said, faster ramp-up time, because that's very important. The time it's taking your application to ramp up is complete wasted energy and resources. And it has a much smaller footprint on load. So very good JVM that's been tweaked for this cloud-native world. Now I'll talk a little bit about GraalVM. So GraalVM is based on Hotspot, but what they wanted, and like I mentioned, this was developed by Oracle and Manchester University in the UK many years ago, which is now kind of, cemented and become a thing. Why is it this different? Well, the difference is it has a new JIT compiler, and essentially what it does is it allows ahead-of-time compilation of Java applications, and it basically allows you to execute native code. It also has truffle language implementation frameworks, and it also allows you to run things like JavaScript. So the project goals of GraalVM were to improve the performance of Java virtual machines languages, so they match the performance of other native languages. To reduce the startup time of JVM-based applications by compiling them ahead of time, to enable Ground VM integration with other services, and to allow kind of the freedom of using polyglot applications, so different programming languages on kind of the same VM or JVM. And yeah, so it's also you can also use lots of different tools with it. So, okay, so it's all great. We picked this runtime, we picked the right JVM, but if we're using the wrong runtime, then it's completely wasted. We can tweak our JVM, we can maximize the performance of our application code, but if we're using an inefficient runtime, we're really not going to get the most out of it. So I'm going to talk about two runtimes here. I'm going to talk about OpenLiberty to start with, because that is the project I work on, so of course I've got to mention it. So OpenLiberty was created out of a product called WebSphere. And WebSphere has been around a very long time. It's a very robust product, like the JVM. We have customers that have been running it non-stop for like 10 to 15 years, so without turning it on and off. So it does what it needs to do, but it's not really very developer-friendly in some aspects, and it's not really built for this kind of cloud-native world. So start thinking again, startup time, ramp-up time, things like that. We want our applications on instantly, and our customers demand our applications on instantly. So IBM went back to the drawing board. We got loads of feedback from customers, and we basically went and created this great new thing called OpenLiberty, kind of designed for the cloud-native world. So it's a developer-friendly thing. So again, we wanted to make this as nice as possible for developers to use. It's a modular application server, so you start off with nothing and you build on top of it. It has something called dev mode, which is awesome, so fast in a loop, so you don't have to worry about the runtime. The runtime will pick up your changes, and you can essentially just write your code, click save, and that's deployed. It supports we have generally been the first to certify and release Jakarta EE and MicroProfile APIs, and it also supports Spring APIs, so you can use this with Spring as well. Comparing to Tomcat, I think Tomcat will boot up a little bit faster with Spring, but OpenLiberty has nearly double the throughput that Tomcat has. So at the end of the day, you're going to use half the containers and half the runtimes than you would if you used, say, Tomcat for running Spring. Also has zero migration and things like that. So we want people to be at the forefront and use our latest specs and our latest technologies. So zero migration is great. So it means our customers and people that are using this project can move up to the latest version, hopefully without their code breaking. Container optimized. We were the first product, I think, in IBM to have an official Docker image. That is what I did when I first joined IBM. I was working on the OpenLiberty containerization team. It's designed for DevOps, so again, taking all those cloud-native characteristics and allowing you to very quickly get stuff through your pipeline into production. Efficient memory usage, so it has a self-tuned thread pool, things like that. So like I mentioned, just enough application server. You pick the specs you want. It starts off very small. I think it's less than 100 meg, and then you add in the functionality and the features you require. Like I mentioned, we were like the first to commercially support, the first to certify for lots of different specs. So MicroProfile Jakarta EE. Right, so that's OpenLiberty. And now I'm going to talk about Quarkus. So Quarkus is another amazing runtime. This is from Red Hat. Very similar goals to OpenLiberty. So you want very simple configuration, like what we've done with OpenLiberty. Live reload, so like I mentioned, being able to change your code without having to save things, having it automatically deployed. Streamlined code, so for 80% of common usages. And this has native execution. Now, I didn't mention this before. Native execution has benefits, but it also has disadvantages. The performance of native code is not as good as if you were running just normal code on a JVM. But of course, it provides stuff like fast startup. So I'll get to some of the solutions that we can put into our stuff after this. So let's have a look at kind of the startup of Quarkus. It's very quick. Like I mentioned, using native code, it can start up ridiculously quick. But like I mentioned, native code has bottlenecks, performance bottlenecks. Some things don't work, like the hibernate function, etc. There are also lots of other runtimes. So I know I've just mentioned the two that are mutually beneficial for me to talk about, but there are others. So do have a look around, depending on your usage and what you want to do. There's probably a runtime there that will support those needs. So kind of moving on to what this talk is about, so tweaking the JVM, things we can do as developers to improve our code, to improve the performance of our code, to make it more robust, to save some energy and save some money on the cloud. So the main things to get the most out of your JVM, first of all, as developers, write efficient code. If you want to get the most out of your JVM, make sure you write code that is efficient. Second of all, pick the right JVM for your needs, like I mentioned. Third of all, pick the right runtime. Fourth, use profiling. Profiling is amazing. It essentially allows you to have a look at what's going on inside your JVM. And then, of course, tweak your JVM. There's lots of different ways you can do that. You can tweak your garbage collector. You can add extra functionality, which I'll talk a little bit about later, and try and show you a demo. So writing efficient code is the first one. Use primitive types where possible. This is an easy way to avoid overhead and improve the performance of your application. Is to use primitives. It's better, for example, to use an integer or a double instead of the large double, because basically the JVM will store the value in the stack instead of the heap. And the stack is a lot more, this has reduced memory consumption, and it can handle basically the primitive types a lot more easily. Use things like the string builder and use string builder rather than string buffer. String builder is really great, but it's not thread safe. So it is more performance, but it's not thread safe. So it depends on your needs, but yeah, that is one way to make your code a bit more performant. Avoid using things like iterators or iterating over stuff. There is loads of libraries out there which can take care of this for you. They are tuned and tweaked and much more performant. So try and avoid using iterators and using other libraries to do the same kind of stuff. And avoid using things like big integer and big decimal. I know a lot of us put that in just to be safe, but it uses a lot more resources. So if you can try and avoid just using big integer and use, say, just integer and stuff like that, it can save you your application a lot of runtime memory. Okay, so choosing the right JVM for your needs. Like I mentioned, there is loads of JVMs out there. The OpenJDK has lots of different flavors you can download. So do honestly check out what the JVM is, what the characteristics of it are, and then check if it works out for you in the right way for your application. Picking the right runtime is another important thing. So here's something that I kind of mapped out. So like I mentioned, Web2 Application Server was great. It was great for monoliths, and it still is great for monoliths. But if you want to kind of scale, that's when it gets a bit tricky. Bear in mind, it might take like 2 minutes, 3 minutes to boot up. So I've got something on here called a microservice. Now, I will try and explain what I think a microservice is. So a microservice, just to clarify, is not a distributed monolith. A distributed monolith is basically a well-architected monolith. It's a monolith we've architected well. What I find a macroservice is when you've got organizations that are trying to break apart monoliths, and they get to a certain point and they go, some of these services are very, very highly coupled. How do I break this apart? And then it gets to the point where it's like, well, I'm going to end up having to rewrite the whole application. And some of these applications, 10, 15, 20 years old, the engineers that worked on this have long gone. Some of them have retired. So breaking apart is very difficult. So you end up in this kind of space of a macroservices, is what I call it, where you've got, say, three highly coupled services together. You can still scale these up and down, so you can still utilize it. Obviously, it's not going to be as efficient if you went down to the microservice or function as a service level. But it's better than trying to run monoliths on the cloud. Then, of course, you've got the microservice and the function as a service. Function as a service is kind of boot up, do its function, shut down. And again, Quarkus is quite good for that because it starts up very quickly. Then you go to so OpenLiberty is amazing because it's built basically to handle most of the workloads Web2 Application Server does, so all the monoliths, but then it has a really fast startup time and things like that. So it's really kind of widespread what you can use this runtime for. So Java profiling, like I mentioned, is really cool. I've been playing around with this. It's quite amazing to see what's going on inside your JVM. They're really useful tools and essentially allow you to look at the bytecode constructs and the operations that's going on. And they can look at things such as your garbage collection, object creation, method executions, iterative executions, and thread executions. It may be a bit daunting at first when you use these tools to have a look at your JVM, but it's quite amazing to see what's going on because as a Java developer, I don't generally look at the JVM. This is just a subject that intrigued me, so I started doing research on it. But do honestly, just get one of these profilers and have a look in your JVM and see what's going on. It's quite amazing. And there's lots of popular profilers out there. I use JProfiler generally, but you've got your kit, Java VM profiler, the NetBeans profiler, and Oracle provides the Java Mission Control one with the Oracle JDK. So do check it out. There will be a profiler that you can use for your JVM. So tweaking your JVM. First of all, tuning your garbage collector. I'm not going to go into detail about that because that's quite a big subject. But do check out online. There's loads of different things out there. I know we're recently doing a video on Expert TV, if you never checked it out, about how to tune your garbage collector. Use the at-in-time compiler, so compile your code ahead of time. Basically, most JVMs have this functionality, so do check it out. I guarantee, well, don't guarantee, but if you look at your JVM, it probably most likely has an at-in-time compiler in there. Enable class data sharing, so this is something that's available on Hotspot and OpenJ9. Hopefully, I'll be able to give you a demo if the demo gods are happy. Probably because I'm live, it's probably not going to work, but we'll try it anyway. Enable idle tuning. So idle tuning is great. Basically, when your microservices aren't doing anything, they can basically lower down the resources they're using. It won't save you money because generally you buy compute units, but it will save energy. So a good thing to try and help save the planet. I'll talk a little about what the JIT server is. This is a new technology. This is quite cool. It means you can basically put your JIT compiler and stuff in a different container, in a different VM, and have that handle it. So your application, the JVM that's basically your application sitting on top isn't doing all the work. And start with a minimum heap size. So don't start too low, but basically just increase your heap size as you develop your application, because generally what we all do is start with a humongous heap size, and that's fine, that works, but it's a massive overhead. So reduce that as much as you can. So start off with something small, get your application to work, and then increase it as you build on your application. So OpenJ9 class data sharing. So this is amazing. Basically, it really helps the startup time of your application. So what is it? Basically, a shared class cache is an area of shared memory, and it's a fixed size, but you can change it. It's a fixed size generally, but you can change it inside Linux. And basically what it does, it takes all the kind of classes that you use in startup and puts it into this shared class cache kind of memory. It cannot grow in size, like I mentioned, but you can tweak that. And you can share this class cache as well. You can restart your JVM and it'll still be there and it'll still work. So basically, it doesn't matter if you shut down your laptop or shut down your machine, the class cache will still remember from before. So kind of how does it work? So normally, when you boot up your application, the lookup order is kind of class loader cache, parent, and then file system. In contrast, a JVM running this technology goes the class loader cache, parent, then to the shared class cache, and then the file system. So it has this extra step, but this extra step provides it with the classes it needs to boot up a lot quicker. It's just a JVM property, so it's very easy to enable this if you have this technology in your JVM. All you need to do is add the -x shared classes. You can give it a name, so different projects can have different names if you're using the same JVM for lots of projects. And like I mentioned, you can specify the shared class cache size in that parameter there. So this is a startup comparison. So this is not using class cache. OpenLiberty is there starting up in 2 seconds. And not just OpenLiberty, any runtime you're using, this technology will help it boot up faster. So if I go into contrast, technology runtimes using the shared class cache, OpenLiberty is nearly halved in startup time. But it's not just OpenLiberty, all the other runtimes have gained a benefit of startup time using this technology. And this is, changing your JVM and adding this option is very simple to do. Imagine if every Java developer around the world enabled this option. We would save energy, we'd save money for our organizations, our customers would be happier because we could scale up and down quicker. So yeah, if you do get the chance and you do have this technology, try it out. And if you don't, then all you have to do is basically switch your JVM, especially if you're using containers, which is quite easy. You just change the from at the top. And yeah, basically you can get the benefits of this. It also, like I said, works in a containerized environment. So going from something like 7 seconds down to 2 seconds. And so we've got a lot of benefit in OpenLiberty because we have invested in adding source code or open source code to the OpenJ9 JVM and into OpenLiberty to really get the performance out of it. So I'm going to try and do a demo now of the shared class cache. Again, bear with me. The thing is, you can all follow along if you want. We have created this online learning environment for you all. Basically, it all runs in the cloud. It's running on OpenShift. What it does, it spins up containers just for you with all your stuff in and allows you to get started really quickly. But I'm going to demonstrate on this environment now. Okay. Move that over there. All right, so it's booting up. So what this is doing now, it's essentially, I'm a user, it's spinning up a container for me. This is running on the IBM cloud in OpenShift on Kubernetes. So it's spinning up the container, which will provide me with Docker, it'll provide me with Kubernetes, it'll provide me with Maven, it'll provide me with the OpenJ9 JVM. And yeah, if you want, you can follow along and do this as well. We also have this environment on our booth, so if you want to try out any different technologies, you don't have to install stuff on your local laptop. You can just click on this environment, it'll boot up and provide you pretty much with everything you need. So I might have to. I can't figure out where my mouse has gone. All right, cool. Okay. So this is the environment. Again, very simple. On the right-hand side, this is where our container is. We have our IDE here, terminal down here, so very easy to get started. I'm just going to change the screen because I cannot see anything over here. Okay, cool. So just to get started, I'm basically just going to clone down a basic repo. You can hit these buttons automatically straight into your terminal. I'm going to go into the finished directory because that means the completed code is in there. And then I'm just going to start up Liberty using Maven. So Maven, Liberty, and then run. So this is without any class cache. This is just Liberty running. It's going to have to download its dependencies, stuff like that, so it might go a bit slower the first time. But while that's doing that, I'm going to go and create the file we need to essentially enable class cache. And I just want to basically demonstrate how easy it is to turn a technology like this on and how we can all do it very easily and basically try and get the benefits from these technologies. So Liberty, we basically have a config folder. This basically gets copied into the container when we start. So I'm just going to create a new file in here, jvm.options. So by having this file in here, OpenLiberty knows when at startup to include this file and essentially take the JVM properties from it and use them on the JVM we've got running underneath us. Again, this is a learning environment, so if you ran this stuff locally on your computer, you'd probably get a lot more faster startup time. So this is nearly started. Give it a second, and we'll see what the startup time is without class cache sharing, and then I'll enable it, show you very quickly how easy that is to do, and we'll measure it again without the class cache sharing. So that started up, as you can see at the bottom, 13.3 seconds. So I'm just going to shut this down, and all I have to do is do -x share classes. It should auto save, yep, just like that. So sometimes, so the first time it's going to populate the cache, but the more you run this loop, the more you run this cycle, the clever it gets. It starts realizing more and more the classes you're using over and over again at startup time, and essentially keeps populating them into the class cache. So you'll slowly get more and more of the benefits, and it will slowly improve over time. Now, you can run, basically what you would do is when you're building your application, you would enable this, put it in a container, and then you would put your container on the cloud, because then you would get the advantage of it. So now we're down to 2.8 seconds already. I mean, that is a very big difference from the 8 seconds or whatever it was at the beginning. And if I run it again, the more I run this, the more efficient the class cache gets, and the more efficient the server gets at starting up. So just give it a second. I'm going to pray to the demo gods. Hope the actual startup time reduces. This is a shared environment, so sometimes it can vary, I should say. Let's start up. So basically, like I said, Liberty's modular, so you install the functionality and the features you need like when you start it up. So now we're down to 2.5 seconds. So we've gone from 8 seconds. All I've done is created a file and added X shared classes, and I've already got it down from 8 seconds to 2.5 seconds. And if I keep running this, it will slowly keep reducing. And now this is all running in a containerized environment. This is a learning environment running on the cloud. So if you ran this in your data center or ran this as part of your cloud deployment, it would start up even faster. And I think we've got it down to just about a second now. Say again, sorry? It shouldn't do, no. Yeah, no, it shouldn't do. I mean, yeah, so what you would do, so I mean, if you're changing a class or something like that, you'd rebuild your application, right? So as part of rebuilding it, you would basically, this would be enabled again. You'd run it a couple of times, the build, it'd populate the class cache, and then you'd redeploy it, right? So that's kind of what I would do. Is that answering your question?
Okay, so I mean, would it clear the entire cache?
No, it basically, it doesn't clear the cache. It constantly keeps looking for new classes that are being used quite heavily, yeah, and then just adds to the cache. Now, like I said, it is a fixed size, so it won't grow and it won't shrink, but you can increase the size. So if you have a particularly big application, you can just increase the class cache size. It doesn't make sense to make it too big, but yeah, so basically if you can increase it a little bit, see if you get a faster startup time. If you're noticing the startup time is the same, you probably don't need to increase the size. But it won't wipe it every time, it'll just add to it. Yeah, definitely, yeah. Okay, so I'm going to go back to my presentation, and I've got to figure out how to switch screens again. Awesome, okay. So idle tuning is something that's pretty cool. Basically what it does is when you're not really hammering your resource, or you say no one's trying to utilize your application, then it can tone down how much resource it's using. So if you look at this side, as you can see the points where it's dropped in how much memory it's using. Now, we generally buy compute units when we use the cloud, so it's not going to save us money, but it will save energy. I mean, there's no point of us having a JVM running at full capacity if it's getting no requests. So idle tuning will basically lower the amount of memory it's using when it's not getting requests, and this will save energy on the cloud. Yes, it's not freeing it up for other people to use, but it means we're not hammering the cloud resources as much. OpenJ9 JIT Server, and this is also available in a few other JVMs. This allows you to essentially put the JIT compiler into anywhere you want, put a different VM, different container. So the great thing about this is it allows your JVM to handle constrained environments. There are many reasons why you might have a constrained environment. So it might be you might have a memory leak or lots of different reasons. But if you all of a sudden are starting to utilize lots of resources in your environment, your application can crash. It can become very slow. And what does that mean? It means your customers are going to have a very bad experience. So this is OpenJ9, and OpenJ9 with the JIT server enabled. So if we start with 300 meg, yep, they perform the same. We go to 250 meg, 256 meg. OpenJ9's, it's okay, it's doing all right, but it's going down a little bit. But if we constrain it to 200 meg, with OpenJ9 without JIT enabled, it's really struggling. And that means, our customers, they're gonna, our application's not gonna be able to serve requests. Whereas with JIT enabled, yes, the throughput's gone down a little bit, but it's still managing to run the application, it's still managing to serve requests. And if you've got good monitoring and good tracing and stuff, hopefully an alert will pop up and there's something wrong, and you can go in and try and fix the problem before your customers start getting annoyed. So this is really useful technology for that. It's very easy to enable a JIT server. You can just so a VM sends a request to a JIT server, so you can just enable the JIT server on one, and then use the following commands to start the JIT server on a different one. And again, you can pass this in as environment variables to your JVM, so very, very simple to do. So I talked about some of the different technologies, some of the JVMs that are out there, but are there any technologies that are coming out that could help us? Now, if you were here for the previous talk, I know they were talking about this, and that was the main point of their talk, so I will try and add a little bit to it. But I call this Cryo, which stands for Checkpoint Restore in User Space, and this is a potential solution for allowing full-blown JVMs to get to that kind of startup time that native code does. Because native code, again, it has performance bottlenecks. It can't do certain things that you can do with a JVM, whereas this technology is helping you with your normal code to get to that kind of startup time. This is a feature on the Linux operating system. It's been there for a while. And it essentially allows you to restart your application from a certain point. So depending on where you start the checkpoint, you can start the checkpoint at just after it's finished, your application's finished booting up. You can create a checkpoint there, and it will start your application up pretty much instantaneously. So this technology works even better when you've got bigger applications. You get more and more benefit out of it. So using this technology with a simple application like the one I showed you earlier, which basically just returns JVM properties, we get down from 1 second to about 0.2 seconds. But if you're using an application with a higher startup time, like 4 seconds, even then we can get down to about half a second. So this is an amazing technology that people are working on to basically improve the JVM to get to that kind of startup time that the native code has, but with the same throughput of a normal JVM. So there are some challenges with Cryo, which are being addressed by the community, the open source community, and lots of different people. First of all, lack of encryption. So this is something that's being looked at. Stuff like no address space layout randomization. It can have problems with number generators, but there are other libraries you can use to get around that. Running as a non-root user is a big no-no for people in containers. People don't like that, so that is something that's also being addressed. And also, we need some APIs to back up this technology. We need our runtimes to provide stuff for us that will allow us to use this technology effortlessly. Because we don't want to have to, nobody wants to have to do extra steps when creating applications and deploying them to production. So having this technology and APIs around it by our runtimes will enable us to really take advantage of it without any extra steps from us as developers to actually activate this. So a little bit of a recap of stuff I've talked about today. I hope you've learned something, if anything. Just how to get the most out of your JVM. Like I mentioned, first of all, write efficient code. That is the main one. We're all software engineers, so we should be doing that. Using the right JVM and the right runtime for your needs, because again, if we're using a runtime which is really big or a JVM that hasn't got the characteristics we need from a cloud-native world, this will make our applications inefficient. Use profiling, even if just use it to have a look, just so you can see inside your JVM and just see what it's doing, because we're all using them as Java engineers. And of course, tweak your JVM, tune your garbage collector, enable technologies like class cache sharing, the JIT server. All these things can help us and our applications be more performant. And like I mentioned, not only are we saving money, we're saving our organizations money, but we're helping saving energy. We're freeing up energy around the world for other people to use that are using these clouds. So I'm not a JVM expert. I'm not going to pretend to be. I came up with this talk because I use a JVM all the time, as most of you probably do. And I really wanted to know what we could do as software engineers to save a bit of money, save a bit of energy, and basically get the most out of our applications. Because like I mentioned, Java is a weird one in the cloud world because we have the overhead of a JVM in every container. So what we should be looking at is kind of not only improving our code and using the right runtime, but really picking and finding a JVM with the right characteristics. These are some of the links to some of the materials. So if you want to know more about any of the technologies I talked about here, all that you can find out there. And if you want some references to some of the research I did for this talk, you can go through some of these links. It will go into a lot more detail about some of the subjects and things I've talked about. So that is it for me. You're welcome to ask me any questions, and I'll try my hardest to answer them. And again, hopefully, you've taken something away from this, even if it's just the thought of, okay, I never thought about the kind of environmental aspect of these things. Even if that's the only thing you take away from this, then hopefully it means I've had some impact. So that's it for me. Thank you all for attending, and I hope you enjoy the rest of the conference. Thanks. Do we have any questions? You could ask them here in the room, or you can come up and ask me privately, or you can come to the IBM booth from 12 o'clock till 4 o'clock tomorrow, where I will be helping out there. Yes, over there. How to enable Cryo. So this technology is not even in beta yet. So you can enable it with a lot of weird and wonderful magic. I've seen people demo it, but it's not something that you can just download easily and get started with. Give it to the end of the year, and you will be able to hopefully easily just enable this technology and get running with it. It's not just IBM and companies. A lot of people in the open source space are working on this technology. And I do have a feeling by the end of the year, you will see some amazing stuff come out, which will hopefully enable us to use this technology effortlessly. We don't want to add extra problems to us. We just want to, like you said, enable a command or something like that, and it utilize this. So yeah, keep an eye out for announcements about this technology, but we've been looking at it for a long time, not just IBM, the whole kind of JVM community, and it's this year everyone started to really think about it and to work on it and actually put open source code and get it working. So keep an eye out, and you will see hopefully some more information come about it. But if you want to learn more, just Google it, and there's loads of information about it. If you really want to try and get it working, you can, but yeah, it might be a bit difficult at the time. It might require a little bit of magic, I should say. So yeah. OpenJ9. So Hotspot also has that technology. So it's not just an OpenJ9 technology. Let me just go back. Eventually I'll get there. It's not just an OpenJ9 technology. Hotspot also do provide it as well. But I think those are the only two JVMs that do enable this technology. Again, if you're using containers, just switch your base image to, say, OpenJ9 or something like that. Try it out. Just see if you get the performance and benefits you want. And if you do, then you can kind of make a decision of how you're going to go forward and use it. So yeah, no worries. Any other questions? Awesome. Thank you, everybody.